Welcome to the second plenary talk for today. It's my great pleasure, and I'm particularly glad to welcome and introduce Professor Andrea Serrani from Ohio State University in the US. Andrea has also a very long list of items that characterize your fantastic track record. I just mentioned a few. You were a Fulbright Fellow at Washington University. You got a Doctor of Science degrees in System Science and Mathematics in 2000. And since 2002, you are at Ohio State. You had a number of visiting positions, especially in Italy, in the best university, University of Bologna, University of Padua, and then also multiple summer faculty activity fellowships at Air Force Research Lab. And you are working in many application fields, and your work has been actually supported by several industries, especially in the aerospace sector. And Professor Serrani has also a number of IEEE awards, like Distinguished Lecturer, but especially he is the editor-in-chief of our flagship journal in application, the IEEE Transactional Control System Technology. And he was program chair of the 2019 ACC, and he will be the co-general chair of our CDC this year in Cancun. And I'm sure we will see many of you there. And so you are going to have the same load I have here.
Absolutely.
Okay.
So shameless commerce department, shameless advertisement for CDC22.
Welcome, and we are looking forward to hear your talk.
Thank you. Thank you very much. Thank you very much, Thomas. This is really a great pleasure and a great honor to be here among fantastic colleagues and great friends. And I'm very happy to present to you some of my activities of many years already, mostly originating at the time that Thomas mentioned on my work at Air Force Research Lab. So the title of my talk is Dynamic Control Allocation, which means everything and nothing. I will explain what I mean by dynamic control allocation. And I will present an overview of what over the year has been my understanding of a problem of allocating control actions throughout multiple actuators. So without further ado, let's introduce the subject of our discussion today. We're going to be talking about over-actuated control systems. Now, for people working in robotics or in mechanical system, when one thinks about full actuation or over-actuation, thinks about all the degrees of freedoms being actuated or being directly manipulated by control. More generally, what we mean by over-actuated control systems are systems which possess a larger dimensional input space than the output space. And by output here, I mean variables to be controlled. There is a blanket assumption that we use state feedback throughout, okay? And as always, application precedes the theory. And an over-actuated system has arisen naturally in the context of robotics. So you see many old papers on redundant manipulators and also in aerospace systems. So one thinks about control allocation and over-actuated systems, naturally the thoughts go to aerospace systems. But also the technology has evolved in such a way that nowadays it's very common to see technological systems which are equipped with a lot of redundant actuators. And that's a very good reason why more actuators bear the promise of fault tolerance, reconfigurability. It's especially important in mission critical systems. So marine systems is one of those premier examples, and there is a very long and a successful tradition of control allocation literature for underwater vehicles. But also you start seeing, well, from a long time actually, over-actuation arising in powertrain systems, especially in turbocharged diesel engines with multiple valves actuation, EGR, VGT, and so on and so on. So, as I mentioned, having more inputs than outputs to control give you the possibility of doing perhaps more than simply tracking a set of references in the output, because this redundancy bears the promise of optimizing a set of behavior. But at the same time, as the number of actuation increases and the complexity increases, there is the need to manage such complexity in a way that the resulting solutions are still tractable from the point of view of implementation and from the computational standpoint. So this being a fairly common nowadays setup, let's take a look at how this, let's just give a couple of examples, for instance, of overactuated systems. Because a couple of examples that I'm giving right now gives you a hint that there is perhaps a little more to overactuation than simply having more things to deal with, okay? So the traditional idea of control allocation and overactuated systems stem directly from aerospace applications. So everybody has flown an airplane in their life. And so if you sit by a wing, you see a lot of movable surfaces going on. Of course, one cannot really see the tail effectors because otherwise that would be a problem. But you see that there's a lot of things that moves on when you take off and when you land and when you steer, when the pilot steers the engine. So typically in civilian applications, all these control surfaces generate moments or are thought as moment generating devices, meaning that you have a lot of control inputs aiming at producing the three-body moments around the axis. And typically in civilian applications, the resulting forces called the body forces are actually named the small body forces because, well, they may not be that small, but we think they're small, so we ignore them when we design control policies. Now, this changes dramatically when within the aerospace area, you start looking at more performant type of vehicles, for instance, fighter jets. Now, fighter jets are again equipped with redundant set of actuators, but the type of actuation that results from this control suite is actually very different because now what you have here, you have the presence of multiple surfaces that are typically not seen in commercial aircraft, for instance, canards, and canards are very interesting actuators, so we will talk a little bit more about this later. But you also have, for instance, unconventional actuation capabilities like thrust vectoring, meaning that your thrust is no longer confined in one axial direction as in conventional aircrafts, but as the ability to change angles, so to produce not only a force in the, let's say, X-body axis, but also forces around the other two body axes, which gives you almost 6 degrees of freedom controllability in certain aircraft. Well, of course, almost, because you can't really fly like this. Okay, that's too much drag to begin with. And also you have enhanced maneuverability, which is dictated by the very reason of existence of this type of vehicles. So you see already that within the same type of application, perhaps there is a difference between one way of looking at overactuation with respect to another. So obviously this is not a new problem. It's been around for a long time. And there is a considerable body of literature in that. So if one thinks about overactuation, you say, okay, I have a control problem. I know I can do more. Whenever you do more, you want to optimize what you're doing, because now you have the freedom to do better by having more actuations at hand. So obviously, when you talk about optimization, online optimization, model predictive control is the natural way to go. And then as a matter of fact, there is a substantial body of literature that deals with control allocation and distribution of control efforts by way of model predictive techniques. Our friend Ilya Khomanovsky is one of the main contributors in this area, specifically related to control allocation, but many more as well. So now, what is the pros of looking at solving the problem of control allocation, simultaneous control and optimization through model predictive control? Well, the pros is that in a model predictive control type of framework, we know we can design directly our controller to be mindful of constraints, both in the input and in the state variables. And also is of general applicability. However, at least for me, I don't understand much about optimization. I have to confess, model predictive controllers are quite cumbersome to tune. They don't scale really well with the dimensionality. But the thing that I was very interested is that model predictive control are not modular. Okay, this is something very important for the industry, something that I learned with working with on this project with Ford. Industry spends a lot of time in designing their controller and especially in calibrating their controllers. So most of the cost associated to controller development in industry is calibration of the controller. And now they're very resistant to someone coming and saying, no. Now, okay, you've done this controller, this is very well, but we can do better by, your own favorite type of control. So what the industry would like to see actually is that you provide solutions that retrofit to existing control architectures. And perhaps they can improve on the performance of those original controllers by perhaps exploiting extra control inputs that were neglected or not taken into full consideration. Obviously, model predictive controllers, they embed everything in one piece, if you want, successfully, I have to say, but they do not lend themselves to a modular structure. Also, it's very difficult, at least I find it difficult, to separate the tracking performance from optimization of auxiliary values. Perhaps the premier methodology for dealing with a redundant set of actuator is the so-called control allocation. Control allocation has a long-standing history, started from the work of Wayne Durham for aerospace application, and then it continued on with many researchers. I would like to mention here our great friends at NTNU, Tor Arne Johansen, Tor Inge Fossen, Andrea Cristoforo, who may be in the audience too, has contributed to this sort of things. And Tor Arne and Tor Inge are mostly interested in application in marine vehicles and underwater vehicles. But there is a huge body of literature, and actually Tor Inge and Tor Arne have a very nice survey paper on Automatica a few years ago that I recommend you take a look at if you're interested. So what is the pros of control allocation? Control allocation, I'll explain a little bit later, looks at a very particular situation, a situation where you can actually carve out a square plant model out of your over-actuated system, design a controller for this fictitious square model, and then distribute the resulting control through optimization in the input space. I will be a little more precise later. But what I would like to point out is the advantages of control allocation. So you control first and then you optimize later, which seems to be a very, very sensible approach. But the problem is that this is not generically applicable. So you may have systems for which the basic assumptions on which control allocation repose, and they're not satisfied. So then you wonder, okay, what should I do? Should I reframe my problem in such a way that control allocation can be applied, which we all know it's not a great idea, right? When you have a problem and you have a solution at hand, typically it's not a good approach to massage your problem to fit your pre-cooked solution. And that's actually the motivation that prompted me to look at this problem because of the very nature of the systems I was working with AFRL. One important thing is that in standard control allocation, you optimize only in the input space, and there is no effect on state trajectory whatsoever. So now let's take a look at control application in a traditional way. Okay? So what do we have? We consider a nonlinear plant model, but the nonlinear plant model here is just because I want to be fancy. If you want, you can replace it with a linear model. There's really nothing's going to change. Okay. I know that there's a little bit of geometry in the title of my presentation. It's not going to be any differential geometry. Okay. So the geometry you will see in a linear setting. But the ideas remain the same. Okay. Everybody who says that nonlinear systems are so different from linear systems, they're telling a lie. At least if you're looking at from the geometric point of view, it's just linear system bent. In a certain sense. Okay, so Isidore is going to kill me. Is Alberto in this audience? No, okay, that's good. He left, okay, great. Okay, so we have an affine system, okay? The main issue here is that the control input is higher dimensional with respect to the regulated output, okay? So M is greater than P when M is the number of inputs. But the standard assumption here is that the rank of the input operator, the B matrix, is actually equal to the number of output to be regulated. So which means that you have a rank deficient input operator. And therefore you can factorize the input operator in such a way that you can now redefine a fictitious input, a virtual input. Virtual input is one of those fashionable terminology dating back to the 90s in backstepping control. So you have a virtual input here. And you can now think of this system as being a square system for which you have a plethora of control design methods. And now you have the task of now going back from V, where you have designed your controller, to U, which is where your physical actuators reside. So pictorially, we can represent the situation in the following way. You have your plant and you have your input operator here, G, which is factorized into G1 and G2. And then you decide, you identify this virtual controller V, same dimensionality from V to Z, which means that if you're trying to find, let's say, a tracking controller, this tracking controller is essentially unique, okay? Okay, there's modulo some initial condition you set on the inverse dynamics, but ideally you can think of this as a unique solution to your tracking problem. And now what you do is that you now take the same control that you have devised for the lower dimensional input, and now distribute across the set of redundant actuators through control allocation. And control allocation is typically done by way of static optimization or some type of gradient descent of dynamic optimization. And there's, so you may ask, what is wrong with this picture? There's absolutely nothing wrong. This works very well and has actually led to a lot of solutions which are both imaginative and very elegant, okay? And again, I'm the least qualified person because I'm not very strong in optimization. So, but I'm actually amazed at the type of solutions, and these solutions work, okay? But there is one slight problem. Well, first of all, from my own perspective, I like to see the structure of problems. I like to see the geometry that's behind a certain setup. So I'm always wondering, what are the necessary and sufficient conditions for the solution of a problem? And this comes with the fact that not all the systems that not all the models, rather, that we work with stemming from technological applications fit nicely into this framework. As long as you confine yourself to aerospace and you just don't think of the body forces generated by the actuator, this is perfectly fine. However, when you start going a little bit more fancy or imaginative in your array of set of aerospace vehicles, things change. And I want to point out this super nice object here. This is what is called a modular drone that was conceived by the group at CASI in Bologna, led at the time by Lorenzo Marconi and Roberto Naldi. This is nothing else but a tail-sitter MAV, okay? It has one big thruster here, producing a thrust, and then it has 8 control vanes, control surfaces, and you typically want to control the position of the center of gravity of the vehicle and the heading angle. And you have 9 control effectors, 1 thrust and 8 control surfaces. And you look at the dimension of the output, you want to control 4 outputs, and you look at the rank of the matrix G, the input operator, the rank is 4, bingo, you are exactly in the setup of the traditional, let's call it this way, control allocation problem. But this tail-sitter MAV, as conceived by Lorenzo and Roberto, was not meant to be left alone. It was meant to be, it was meant to be attached within each other's in several modules. So if you now take 2 of those and you connect them rigidly in this way, now you are doubling the number of inputs, which is as expected. You have 2 thrusts, you have 16 control vanes. Of course, you have constraints because otherwise you will rip the setup apart. But you want to control the same thing, okay? Because now this is, again, a rigid body. So what I'm interested in controlling, the center of gravity, the position of the center of gravity, and the heading of the vehicle. But now I have an enormously dimensional input space, again, with the constraints in place. 4-dimensional control output, but now I look at the rank of the matrix G, and magically something happens that the system has gained in the rank of your control matrix, which now starts saying, oh, okay, controllability distributions. So that's something more that you can do now, not just in terms of regulating these four outputs, but perhaps now there's a new direction. But most importantly, the first order outcome of this is that this is no longer within the assumption of the control allocation, because now the rank is greater than the number of outputs to be controlled. Okay, you say, okay, this is not a big deal. I can identify a new output that I want to regulate and go back. But this is precisely what I don't want to do. I don't want just to settle for something that is dictated by my control policy. I want to understand what's happening and maybe perhaps devise a control policy that it's more unifying, okay, that can deal with the previous situation and this new situation in such a way I don't have to reshuffle my control problem all the time. But wait, there's more, okay? So this is the one situation that I was dealt with when I was started working at FRL. What you see here is a pictorial representation of a hypersonic cruiser. Now, there's a lot of unfortunate, for all the unfortunate wrong reason, a lot of talk about hypersonic vehicle these days, mostly in the context of the war that is going on. Well, okay, well, this is AFRL, so they are in the business of building weapons to a certain extent, right? So, but let's take a look at the longitudinal dynamic of this vehicle. This type of vehicles have their own aerodynamic issues. Their dynamics is, although written in the same way, they're slightly or dramatically different than the dynamics of conventional aircraft. But let's not get into many details. But let's take a look at this, at the longitudinal dynamics of this vehicle. This vehicle, so this is the dynamics in the vertical plane. Okay, very simple dynamics comprising the airspeed, the flight path angle, the pitch angle, the pitch moment, and the angle of attack defined as the difference between these two, okay? So what are the inputs here? The inputs are the thrust generated by the scramjet engine and the elevator deflection, well, one of these, okay, the elevator deflection that actuates the moment. So if this was a conventional aircraft, I would say, okay, I'm thinking as the actuator deflection as the principal actuator who generates the pitching moment. And everything is okay. Unfortunately, what you see here, you see that the lift force, the force that keeps the vehicle afloat, also depends on the canard, on the elevator deflection. So when you start looking, you come to look at the system as I did, equipped my Isidori's book, you know, and all these nice concepts, the relative degree, the zero dynamics, all, you know, a young fellow in love with nonlinear control. But you start looking at this and you say, oh, wait a minute, this system does not have full relative degree because I have the control input there, somewhere, right there. And as a matter of fact, if you look at the lift, you can approximate, this is a very crude approximation, okay? Not very nonlinear, I'm afraid, but very crude approximation depends on the angle of attack and the elevator deflection. Now, this presence of the elevator here tells me that the relative degree with respect to this is 1 and 1. And we all know what that means. It means we have a non-trivial zero dynamics. But unfortunately, then when you apply the decoupling feedback, the resulting zero dynamics is unstable, okay? And therefore, that's a problem because, well, we don't like to see unstable zero dynamics because we like to, you know, do some sort of linearization by feedback. That's our one-on-one control approach. Okay, so how do we solve this problem? Yes, of course, you can devise very complicated nonlinear control strategies that deal with non-minimum phase zero dynamics. There is no general solution to that, which is good if you have a good graduate student, because that's a good problem to put your graduate students to work on, and eventually they'll find a solution, otherwise they won't graduate. But apart from that, the Air Force is, you know, very gung-ho on solving problems. So we'll say, okay, let's equip this vehicle with a non-conventional actuator, which is a canard. A canard is this additional control effector that is put on the fore of the center of gravity. Now, what a canard does, it changes the controllability of the vehicle in a very fundamental way. And, well, not really, but I'll explain why. So basically what you have now, you have two surfaces. It's no longer just an elevator, but also a canard. And the canard enters in the same forces and moments as your elevator. So now you have two surfaces to play with. And obviously what the aerospace people do okay, let's just design the canard to get rid of the elevator contribution on lift. This is called ganging of the surfaces. So basically what the elevator does, the canard does in the opposite direction, so that there is no more contribution of the elevator to the lift force. And for us, control people, this means now that, no, come on. But, okay. This means now that the system has full relative degree. Of course, you need to add a little bit of dynamic extension. The system is now fully linearizable by feedback. You cannot really fully linearizable because you don't know the dynamics, but that's a different story. From a structural perspective, you gain full relative degree and you're super happy. Okay. Great. Now, this is a new example to draw inspiration from. And if we all come from the same boat. We are not just happy with the technical solution to a problem. We want to understand what's behind the technical solution to the problem. So structurally, what is the deal with over-actuated system? By structurally, I mean from the point of view of the geometry of your system, what is going on in the system when you have more inputs than outputs. The first thing that comes to mind, if you look at the previous example, oh, great. I didn't know how to stabilize the system first. I had the canard. Now I know how to stabilize it. Therefore, over-actuation has all to do with stabilizability. No, it has absolutely nothing to do with stabilizability. Okay? And in the previous problem, the aerospace vehicle, the problem is us. It's not the system. The problem is that we don't know really well how to control non-minimum phase, non-linear systems. But that's nothing to do with the amount of inputs that you have. Of course, if you don't have enough input, there's nothing you can do. But there's something that we have understood from the previous example, and this is the key, in my opinion. That when you add the canard, you're not changing the fact that you can stabilize the system, because you look at the first approximation, the system remains stabilizable with just the elevator. What you did, you changed the structure and infinity of the system. When you go from relative degree 1,1 to full relative degree, what you actually happen is that you remove the zero dynamics. Thinking linearly, okay? Let's think linearly, because there's no way you can understand anything if you don't think linearly. Now, this may come to a surprise to you, but perhaps not the old timers in the audience. But controllability is a generic property for linear systems in the space of parameters. Meaning that if you have a system that is non-controllable, that's an oddity, that's a singularity. It's an open property in the parameter space, controllability. And it has nothing to do with how many control inputs you have. You only need one control input. And as a matter of fact, many of us remember that there is a technique to control multi-variable linear system by applying a preliminary feedback. So you make the system controllable with just one input, and then you apply Ackermann formula. Is that a good solution? Probably not, but it's a solution. So controllability is generic, has nothing to do with how many control inputs. But what you see from the HSV example is that the canard has removed the invariant zeros of the system. Without the canard, you have that your largest controllability subspace, which is basically the set of trajectories on your zero dynamics that are controllable, is zero, because you don't have any more control inputs than the one you need for do tracking. And as a matter of fact, what you have is that your zero dynamic is, well, there should be isomorphic here. I apologize to all the geometrists and algebraicists in the audience. So your zero dynamics is actually isomorphic to V star modular star, which is the subspace where of the factor space where the induced map has unmovable eigenvalue. Basically, these are the zeros of the system. And that's where the zero dynamics tells you that, well, this is no minimum phase. When you add a canard, what happens is that your zero dynamics becomes fully controllable. Okay, so your system remains stabilizable, your system remains controllable, but now you have extra degrees of freedom to move the invariant zeros. And therefore, you can assign eigenvalues to what was previously an unassignable dynamic induced on the factor space. Aha. Which means that overactuation fundamentally has something to do with the zero structure. And when you think about zero structure, you think about the zero dynamics. Now, we all know that the zero dynamics is a very powerful concept for stabilization. And we have countless applications of zero dynamics. Backstepping is zero dynamics, is redefining the zero dynamics at each step. But there's one thing that the zero dynamics, that is the true essence of the zero dynamics in the system. The true essence is the right inversion of the system. Now, when you do tracking, you have to do two things. You have to generate a motion in your system that produces the output that you want. And then you want to stabilize that motion. So there is no escape when you solve a tracking problem from solving an inversion of your model from the right. So let's recall what is the right inversion of a system. You are given a reference in the output. You want to find all pairs of initial conditions and open loop inputs such that when you initialize your system at the right initial condition and you apply the right input, magically your system reproduces in output the reference trajectory that you want, okay? And that's precisely what it's written here. So now the connection is starting to unfold. More inputs does something to your zero structure. The zero structure is intimately connected to your right inversion of a system. But now let's see what are the implications of redundancy, m greater than p, not on the plant model. I'm no longer interested in the plant model. I'm interested in the inverse, the right inverse of the plant model. So now we have all the different situations that are possible. The number of inputs is greater than the rank of the input operator, but the rank of the input operator is equal to the rank of the output map, the differential. Think about the C matrix, doesn't matter, which is equal to P. This is precisely what Luca Zaccariani in a nice paper in Automatica called the strong input redundancy, and I shamelessly use his terminology here, although Luca did this for linear systems in transfer function form. This is precisely the situation of the traditional control allocation. The second situation, Luca calls it weak input redundancy. Now you have a full rank input operator, same number of input as the rank of the matrix B or G, but this is strictly greater than the rank of the output map, which is equal for, which just take it equal to the number of outputs. This is a situation precisely where traditional control allocation cannot be applied. This is not what happens. And then you have a general input redundancy, which is the two of them combined. This, number 3, is the multiple drones of Lorenzo and Roberto. The weak input redundancy is the case of the hypersonic vehicle. Of course, there is an uninteresting case, which is the one that the rank is less than the rank of the output, but this means that the system is not right invertible, so we don't care. I want to point out, again, let's go back to linear systems, that linear systems possessing a matrix B with rank greater or equal than the rank of the matrix C are generically right invertible, meaning that if it's not right invertible, it's a real oddity, okay? And it's just a singularity in the parameter space. So now we understand that overactuation is intimately related to right inversion. That's the right notion to think about when you think about overactuated systems. Now, there's also a standard trick. Now, I want to pause for a second. Having built this connection suggests that if I have more inputs than outputs, I will have some freedom in choosing my right inverse, and that's precisely the case. And the question is, how do I compute my right inverse? Oh, there are standard methods, Silverman inversions method, so on and so on. But you can also use a trick. Right invertibility is invariant with respect to state feedback. So what you can do, you can apply a fictitious feedback to your inverse, compute the inverse for this new system that's fictitious, then revert the transformation, and bang, you obtain the inverse for the previous system. And the question is, why on earth am I doing this? Why am I complicating things? Can I just simply compute an inverse for my original system and get over with it? Well, this feedback that you apply preliminary helps you or may help you unlocking the internal structure of your right inverse. You can do anything with the feedback, right? But in in our geometric understanding, we know that certain feedbacks are better than others because they are friends of certain subspaces. Meaning that, very simply speaking, A plus BF will contain a lot of zeros all of a sudden, right? So you know, okay, this subspace is invariant. This matrix is factorized in a way that I know that this thing does that, I know this thing does that, so I can sort things out. It's like when you take your closet, it's a big mess, and you start putting all your stuff in order. That's precisely the spirit of applying a feedback, which is a friend of a manifold. Now, the type of feedback you want to use depends on the type of redundancy. For strong redundancy, it doesn't matter because all your redundancy is in the input space. All you do is basically navigating in the kernel of G, so it doesn't matter. But in the weak redundancy, you do want to use a particular feedback, which is the friend of either the largest controllability subspace contained in the kernel of C or the largest controllability distribution contained in the kernel of DH. Translated into understandable language, it means that you create a lot of zeros in your maps, and you just sort things out. And of course, what you do when you have a board or an audience that's already bored, and you want to impress them, you put a commutative diagram, right? This is a standard device for people to, wow, that's a commutative diagram. Yeah, we have a commutative diagram. So let's take a look at the case of linear systems, because we don't want to deal with the differential geometry stuff. So if you look at strong redundancy for linear time invariant systems, remember, this is the case where you have essentially that you have an input operator which is rank deficient, but then the rank is equal to the number of outputs. So what you do here, you simply have a kernel of B, and you know that any input in the kernel of B will not reach the state space because they end up in the zero map as a kernel, and therefore will never affect the output. Okay, no matter what type of feedback you're using. But then you can factor out the kernel of B and look at a reduced system defined on an input space, which is the input space modulo the kernel of B. This system down here is a dynamical system, and it's a square system. So you have a unique inverse for this lower dimensional system, and then you have all your degrees of freedoms are in the input space. And your strongly redundant system is essentially just a memoryless map, the zero map from kernel to X, and then you can resolve redundancy simply by a canonical projection modulo the kernel. But when you have weak input redundancy, this is precisely why you want to use a preliminary feedback when you build the inverse. Because it's only when you use a preliminary feedback, and the feedback is a friend of your largest controllability subspace contained in the kernel of C, that you unlock the structure of the inverse. Now the structure of the inverse is displayed, and it's displayed precisely in the same way. You have an upper subsystem which does not affect the output, okay? And you have a lower subsystem which lives in a factor space. And that system is square. So if you want to compute an inverse, just look at this. The inverse is unique, you're good to go. But the top subsystem gives you all you can do in the inverse in addition of the one you necessarily have to compute. So the top subsystem is now a dynamical system. That's the difference from the previous case. In the previous case, the redundancy was just in the input. Now you have a redundancy in terms of forced trajectory, which are controllable trajectory, evolving in a subspace which has been made invariant by an appropriate choice of feedback. And this system, all these trajectory are unobservable from the output, meaning that whatever you throw in here it's not going to affect your inverse. And I mind you, I'm not doing anything to the planned model. So I'm still using the controller that Ford has given me because it cost them like $20 million, and they don't want you to mess with it. I want to show you a couple of pictures, which tells you precisely which shows what I'm telling you. The case of strong input redundancy. That's the inverse, okay? So you have a reference trajectory in the output. There's only one trajectory in the state space which reproduces this trajectory in the output. Only one. Okay? And this is created as a motion of your system by an appropriate control. But this control is now, you have an infinitely many choices of this control. And this is basically the equivalence class modulo the kernel of B. So one reference in the output, only one reference in the state, multiple many, infinitely many references in the input, meaning that your optimization lies there. That's control allocation, the standard traditional control allocation. Now, the other situation, the weak input redundancy, is different. Now, in correspondence to one output trajectory, you have infinitely many state trajectories which can reproduce this function as an output of the system if you're forcing the input by the correct input. One output, infinitely many trajectories. For each one of this trajectory, one input, and only one input will produce this as a motion. You can skip the middleman, think of this as optimization in input space. Not really, that's not the best way of looking at it, because now you have the possibility of choosing the best trajectory for a purpose in your state space rather than input space. Confined to a subspace, confined to a submanifold, of course, but then you can do perhaps more. You can throw in constraints in your state space as opposed to just the input space. And that's how you should be looking at the solution, in my personal opinion. When any tracking problem is solved by a 2-degree of freedom controller, there's no escape to it. If you want to do tracking, you have to have an inverse, a right inverse, and you have to have a stabilizer. But that's how our interpretation differs, because a stabilizer, you might as well use a fixed stabilizer. You can square the plant, you can do whatever you want, choose a stabilizer that it's better. When you do LQR, do you really care how many control inputs you have? No, you have a really good way of assigning the control inputs. You just select the weights on your R matrix, and then you're good. So, okay, I have certain actuators which are slow. Okay, then I add frequency weighting. It's great to see a young audience, but when I was young, the H infinity church was predominant, right? So we all learned about frequency weighted optimization in H2 and H infinity. Okay, so well, you have slow actuators, you have less powerful actuators, just weight them, design your stabilizer, and you're good to go. And you take the stabilizer from form, for crying out loud, right? But now what you can do is in this guy over here, you can exploit the redundancy, not in the stabilizer action, but in the generation of the inverse. And now you can attach a mechanism that forces those controllable trajectories or the redundant trajectories in the input space to steer the system in an evolution that it's more convenient for your constraints, for your energy, while at the same time continuing to produce the trajectory in the output that you want. That's the beauty of the redundancy in the inverse system. Because whatever you're doing here, you're not changing the fact that your system is tracking the same trajectory in the output. It lives in a big factor space. And most importantly, tada, you have a plug-in structure. You have something you can add to your existing control input by managing the reference. Now, how do you effectively manage this reference? In linear systems, well, linear systems are easy. If you go back to that incomprehensible commutative diagram for comprehensible for Thomas. Now, Thomas has seen this commutative diagram for a long time. He's growing the beard because of my commutative diagram. But for linear systems, it's very easy. You look at the commutative diagram, the maps are right there. All you need to do is apply a change of coordinates, do a little projection. Everything is fine. For nonlinear systems, there's no escape from a normal form. Okay, so if you're lucky enough that you have a well-defined relative degree, you look at the Isidori-Burns normal form. If not, the system is right invertible. You can use other quasi-normal forms. Silverman's algorithm. There is a very nice book by Alberto, a recent book that deals with exactly multivariable nonlinear systems. So there are techniques to find normal forms, but at the very end, okay? So let's cut down to the chase. In many situations of interest from a technological perspective, your inverse is made of two parts. And this is the inverse for overactuated system. Note that you have an X-ring. There is always an algebraic part where the reference in the state space is related to derivatives of the output. Flatness, okay? That's akin to flatness. And then there is a part which is dynamical, and that's where your redundancy lies. Think about the redundant system defined on R star. That's where you want to do optimization in the reference state trajectories. This system right here, the dynamical part, contains and generates all controllable trajectories of the right inverse. This is, for those of you who are familiar with the geometric jargon, these are all the trajectories belonging to R star, governed by the restriction of A sub F to R star. But for us, this means that you can modify the trajectories of this part of the inverse without influencing your output. But by doing that, you're changing the trajectories of your stabilizer in a completely transparent way. So perhaps you're not going to hit the constraints as much. And now, that comes the dynamic part of your control actuation. So let's recap for a second. We have seen that we can actually rethink all the overactuated system framework into thinking of redundancy in the right inverse. I know that I can generate multiple trajectories in the input space and state space in the inverse that keeps me the output where I want it to be. How do I change this trajectory? I need some sort of parameterization. Well, let's assume we have a cost function that we want to minimize. And we want to minimize this cost function by selecting at each time instant the best reference trajectory, the best steady state motion that gives me the minimization of this function, or at least goes towards minimizing this function. First of all, I need to resolve the dynamic constraint imposed by the controllable trajectories on the inverse dynamics. What do? Well, I use flatness. Okay, I use flatness. What is flatness? Well, the 101 idea of flatness is that this is dynamic. It's just the same as, well, roughly speaking, the same as having full relative degree in your system, possibly through dynamic extension. Sepulchre was looking really bad on this. Possibly through dynamic extension. So what do? You look for an output map, a fictitious output map, such that your resulting dynamics on the zero dynamics has full relative degree, meaning it's differentially flat. At this point, you parameterize your solution on the zero dynamics as this deviation from a solution which is a steady state solution. So you pretend that everything is constant, okay, and then you parameterize your trajectories from the solution of a regulator equation. I had to put a regulator equation, okay? So it's so dear to my heart that a regulator equation must pop up every once in a while. But this is just a way of saying, okay, so everything is constant. I know precisely what the parameterization is, okay? But things are not constant. I want these trajectories to evolve. How do I make them evolve? I make them evolve through a good old gradient descent, okay? But these trajectories are not constant. Yes, of course, they're not constant, which means that there would be a dynamics in the system in closed loop. But wait a minute, I have a gradient gain here. And of course, I'm not going to bore you with the details, but you can prove that this interconnection between your allocator and your inverse dynamics, the controller couldn't care less, because the controller, everything that the allocator does is in the kernel of what the controller does. But there is a feedback loop between your inverse model and your dynamic allocator. But if you keep the gain not too high, you can invoke some 2-time scale behavior or small gain arguments that makes this work. And let's see some examples, okay? I have, gosh, I have 7 minutes left, 5 minutes left. Okay, so I'm gonna. Okay, so Two examples from aerospace research. Okay, I had the pleasure of working with a very talented aerospace engineer, Raffaele Baggi. I was a student of Elisa Franco. We collaborated. It was a Riverside at the same time. He's super strong in aerospace, in air vehicle design. So we designed a prototype in simulation model of what we call a swellodrone. This is a conceptual over-actuated aircraft. An aircraft that has multiple actuations or multiple actuators on the wing and the tail, and also a canard. So here you have a throttle input. You have 6 aerodynamic surfaces: a right canard, right flap, right tail, left tail. Now, we have a standard vehicle dynamics. I'm not going to go through this. These are standard Euler equations. What I want to point out is that we have a thrust input on the axial x direction. We have some body forces produced by the canard. That's important because that's what gives you the weak redundancy. And we also have the controlled moment generating from all the other surfaces. Now, what we have that all the aerodynamic effectors have constrained dynamics. As usual as you have in aircraft. You have rate limits, demand limits, you have a dynamics. You also have that the forces and the moments are parameterized by the effectiveness of the actuator. So if you lose a part of an actuator, your ability to generate a force is decreased. And you don't know about it because nobody's looking at the actuator. So unless you have a dedicated fault detection and isolation algorithm that tells you, well, look, you're thinking you're producing this much G-force, but you're actually not, okay? And as a regulated output, we have the usual airspeed. We want to keep the side slip angle to a bare minimum, and we want to regulate the angle of attack and the turn rate. Now, this is the reconfigurable flight control architecture. It's a very pompous name, I agree, but it's comprised of your guidance system, whatever it is, your adaptive controller, that's a standard adaptive controller for your uncertain dynamics. And then the reconfigurator capability is given by a mechanism that estimates the effectiveness of the actuator. That's what I was talking about. You estimate the effectiveness of each single surfaces. So perhaps if you have reduced effectiveness, your algorithm will estimate it. And then you have a dynamic control allocation. Now, the first reconfiguration capability is done by the estimation of the actuator effectiveness. You can do this by, basically, this is nothing fancy. It's just indirect adaptive control. But then you have the dynamic control allocation. The first is the one that deals with this strong redundancy. Okay, the kernel, those free trajectories in the kernel of the input operator with the estimated effectiveness. And this is a gradient descent. And the cost function is the difference between the actual deflection of the actuators and the one you command. Why is that important? Because that's the actuator dynamics in between. Okay, so if the actuator saturates, there is a difference between delta and the delta command. And we want to move along the input space in such a way that this difference is minimized at all times. So from the point of view of the pilot has the impression, or we would like the pilot to see that the force he commands is the force that he receives. And the effect of the actuator dynamics is minimized. And this is in optimization in the input space. But wait, that's more. We have weak redundancy. We can assign by canard, actually 3 minutes. We can assign by canard the angle of attack. The angle of attack is the weak redundant state trajectory. And now we can actually change the angle of attack continuously in a way that we put our forces in the best situation to produce what we want. Remember that forces and moments depend on the angle of attack. So if you don't care what the angle of attack is, because you can control it to a certain extent, you can put yourself in the most favorable situation to perhaps remedy certain deficiency by arising from faulty actuators. And those are the results of simulation, you see here that we have 3 damaged actuators. One fails at 10 seconds, the tail fails at 40 seconds, one of the ailerons fails at 70 seconds. Now, what the instability you see here is because if you only use adaptive control, you cannot recover from these 3 types of failures acting at the same time. But you add your redundancy, and then your reconfiguration does the job. And last thing I want to show, we have some tests on a scaled down model. This is, again, the work of Raffaele. We have here a scaled down system where the redundancy is only strong, but it's in the roll angle axis. And we have proven, from flight the tests, that you can fail the aileron at any time, and then the flap reconfigure itself to do the job of the aileron. But most importantly, this is done without any fault detection and isolation algorithm. Simply by looking at the commanded deflection, the actual deflection, the algorithm figures out what to do. Last slides. Well, this is BS. What I want to show is how many people have contributed to this throughout the years. I'm very grateful to have been working with a number of talented individuals listed here, and especially the students at postdoc at the very top. Sorry for going a little bit overboard. Thank you so much for your attention. Send me emails if you want to talk about it. If you want to ignore it, that's fine. We're all good friends. I understand. Thank you so much.